Hey programmers, Alvin here. Right now I want to go through a Python solution for this tree includes problem. And so in this problem, we're going to have to really just implement the classic and go-to solutions for a breadth first search and also a depth first search. We'll start with breadth first. And of course, to do that, we're going to need to use a queue. If I want to do this in the most optimal way, I'm going to use Python's built-in deck to give me an optimal queue implementation. So I'll say, I don't know, from collections, import the deck. And I'll start by checking maybe whether or not the root is none by default. So if my root is none, and I believe that is an actual literal test case, but if the root is none, can you find the target in the empty tree, right? Because none represents the empty tree. The answer is no. So just return false. Cool. But beyond that, I can write my general code, and that means I initialize my queue. So I can say queue equals deck. And I'll initialize it with just the root inside. Cool. So again, if you wanted to, you could use just a plain old Python list as your queue, but in terms of the runtime, that would technically be an O of n squared solution in the long run, because removing from the front of a Python list is n steps, right? But if you move from the front of a deck, you're going to get O of 1, which is nice. And so we'll begin our main loop by iterating while our queue has stuff on it, right? So while my queue is not empty. And I'll begin an iteration by just removing the front of my queue. So here's where my deck comes into play. I can say queue.pop left removes the front of my queue, and it'll return it to me. And I'll call that my current. Nice. And then from here, what I want to do is check this current node, right? So I process a node typically for me whenever it leaves my queue. So at this point, something just left my queue, and I'll check if my current value, so current.val, that is, if that's equal to my target, then I've just found the thing I'm looking for. So just return true, right? I can just return true early, and I don't need to look through the rest of my tree because I've already confirmed that I found the thing, right? No point of continuing. But let's say this if statement is not true, then what I'll have to do is just add my children into the queue so I can travel through the rest of my tree via a breadth first order, right? So I can say queue.append, and I'll append my left and right children. So root.left, and likewise .right, and here I really mean current, right? But I need to be sure I only append those respective children if they exist, right? So something I always think about is, imagine I had an asymmetric node, like for example, this C node. The C node has no left, so its left is none, but it has a right. So I need to check those two children independently before I add them. So I'll just guard with some if statements here. So I'll check, hey, if current has that type of child, then I'll append it, and I'll make this one right. So for the most part, this should look like very familiar code. So like this is pretty classic, and so is this. The only thing new right now is this conditional, right? If I find the thing I'm looking for, then return true. Now this begs the question, where should I return false? And the key is to return false after you're done traveling through the entire tree, right? If I finish looking through the entire tree and this if statement is never true, that means I didn't find the thing I'm looking for, so I can just return false. Cool. The incorrect thing would be to just write, like, I don't know, an arbitrary else statement here and else return false. I know that this code is just suspicious because no matter what, on the first iteration of your while loop, you're going to just exit out. You're either going to return true or false. In the case of you not finding your value immediately at the root node, you're just going to return false, but you didn't look at the rest of the tree, right? So none of that. You want to do a late return false here. That's a pretty common programming pattern, right? You iterate through some things. If you find the thing, return true early. If you don't find the thing by the end of the iterations, then you return false. Should be nothing new. But with that, let's go ahead and test this code. Nice, and there we have a breadth first solution for this tree includes problem. All right, so here's what we'll do. I'll also show you how to solve this one recursively, which would be some type of a depth first style, right? So we'll redefine this function. I actually am quite a fan of the recursive version, and you're going to realize that a lot about me as we go through all of these problems together. I just feel like the recursion is so elegant sometimes, right? So I'm going to take in the root and the target, and I'll start with my base case. And I think you always should start with the base case. There's not a time where starting with the recursive case is easier in my opinion, right? So for my base case, I think about the simplest form of the input. So I know that a root is going to represent like the root of the tree I'm given. What's the simplest tree I could be given? Well, it's the empty tree, right? And programmatically, that means if my root is none. So if my root is none, then what should I return, right? I need to return some value here. And so if root is none, that means I have an empty tree. Could I find the target in the empty tree? The answer is absolutely not, right? You can't find anything in the empty tree. So just return false. That will serve as like my base case, right? I'm going to need another base case here, right? What if the target I'm looking for is immediately at this current root that I'm at? So if root val is equal to my target, then I've just found the thing I'm looking for. So I can stop here and just return true, right? The target is indeed found within the tree. So those are my two base cases. So notice I have two of them here. And now I'll think about my recursive case. So let's say I'm not, super certain in my brain, how I need to actually write the logic here. I know some patterns must be present, right? So I'm solving this recursively. That means, well, no duh, you're going to call the same function, right? And now that I'm calling this function, it's at least recursive, right? And I'll think about what arguments I pass in. Well, I need to look within my left subtree so I can pass along root.left. And the target never changes, right? For example, if I look at my example 1, if I'm looking for E, that target of E never changes, right? I'm looking for E everywhere in the tree, right? And so I pass along the same target. I'll do something symmetric for the right-hand side. Cool. And I will do my recursive leap of faith, right? I ask myself, what type of data do I get back from these respective recursive calls? I get back a Boolean, right? Telling me whether or not I find the target in the left subtree or if I find a target in the right subtree. Cool. And then from there, if I get like true or false from these respective calls, I really just want to OR them together and just return that value in line. So if I find my target in either the left subtree or the right subtree, then return true. Cool. And notice that if I don't find the target in either, so they're both false, I say false or false, and the entire thing evaluates to false. This logic is good to go, and I love how compact this code is. So I'll give it a shot. Always want to be sure I test my code. Cool, and there we have our recursive solution for tree includes, right? So I recommend that you practice both implementations. So do the iterative breadth first solution, do the iterative depth first solution if you want, and just use a stack, right? But also be sure to practice the recursive depth first version, right? Having all of these different strategies under your belt is really going to open the door for solving much harder problems down the line. And I do consider this type of recursion a very, very, very core pattern, right? It really shows an understanding of how I can take a large problem, right, into subproblems, how I can take this large tree into many subtrees. Cool, so practice this, and I'll catch you in the next one where we're going to switch things up.